Precipitation reactions, these are things that students really do struggle a little bit with at GCSE. So let's try and use some visuals to work out what's going on in a precipitation reaction. So we take a solid substance such as silver nitrate. Now silver nitrate is ionic, so you can imagine that the different coloured circles here represent the individual ions, of which there's only two present in the compound. You've got a silver Ag+ ion and a nitrate ion, and as a solid they're regularly arranged so that all the positive ions attract all the negative ions around them, so they are in order in a lattice arrangement. And the same could be said of any ionic solid. So if I were to take sodium chloride, we could draw the same kind of diagram where the different colours represent the sodium ions and the chloride ions. So that's in solid form. And in solid forms, we can't see through those substances. The lattice will scatter the light back to us, so we see them as opaque. Okay, so what happens when we take that silver nitrate and we put it into water? Obviously this is not to scale, those particles would be much smaller, and what we can't see is we can't see the water molecules. So remember, there are lots of water molecules all in that beaker. We just haven't drawn them in to make it look a little bit clearer. So you can see that all the silver ions and the nitrate ions have now separated, and that solution would be colourless, but it would also be clear, so we could see through it. It would be transparent because there is no longer a solid there. The particles have all spread out from each other. The same can be done with sodium chloride. So silver nitrate is a soluble solid because it's a nitrate. All nitrates are soluble. Sodium chloride is a sodium salt, and all sodium salts are soluble. In it goes, and now we have a transparent solution of sodium chloride. So actually it would be more accurate, instead of writing AgNO3 as if those ions are stuck together like they were in the lattice, we could write it as we've shown in the bottom there, where the silver ion, the Ag+, is actually separate from the nitrate ion, and they are both separately dissolved. So they are no longer ionically bonded, they're no longer attracted to each other, they're actually attracted to the water molecules instead. Same is true for the sodium and the chloride ions, and so we could write them separately. So both of these ways of representing it are accurate. If we were doing it in equation, we would probably simply write NaCl brackets aqueous because it's easier. It's just quicker to write it that way. But remember, it always means that the ionic bonds are broken and that the ions are separate. So how does this relate to precipitation? Well, if I take these two solutions and now pour them into the same beaker, that is when precipitation happens. And it happens because silver chloride is an insoluble solid. So when the silver ions, the red ions here, come into contact with the chloride ions, which are represented by the orange ions over here, then they will stick together because their ionic bonding is too strong for the water molecules to push them apart. It's a bit more complicated than that, but we don't need to go into that detail at this stage. So if it's insoluble, the ions will stick together when they meet in solution. That's now forming a solid lattice like we had at the start. That is now something which will scatter light, so the solution will appear now cloudy because it will have solid particles in it. It won't necessarily form a nice layer at the bottom of the beaker. It would if you left it over time. Meanwhile, the sodium ions and the nitrate ions have not actually done anything. So we took these separate ions at the start. The silver ions started in solution and they ended in this solid precipitate. The chloride ions started in solution and they ended in this solid precipitate. So they've undergone a change. They've gone from being in solution to being solid. The sodium ions started over here in solution, but they haven't changed. So these blue ions here are still floating around. There's no chemical difference at the start and the end of the reaction. And the nitrate ions here, the little green ions, they haven't changed either. And so therefore those nitrate ions are still aqueous. They started aqueous and they ended aqueous. So this is how we decide how to do the ionic equation for this reaction. These sodium and nitrate ions are known as spectator ions. They're not doing anything. They're not undergoing a chemical change. They have the same charge. They have the same state. They're both aqueous, start and end. Nothing's happened to them. So actually the chemical reaction only involves the silver ions and the chloride ions to make silver chloride. I'd see the same thing happening if I used potassium chloride instead of sodium chloride. Sodium's not involved. So I can write an equation that only involves the silver ions and the chloride ions. So the silver ions were in the first beaker in solution, the chloride ions were in the separate second beaker, and when I mixed them together they both came together to make a solid, which is my precipitate. So this is an ionic equation, and it leaves out spectator ions, only includes anything that's undergoing a change, and in this case the change is a change of state from aqueous to solid, which is always a mark when you're writing this type of equation. So let's go through some examples of writing ionic equations for precipitation reactions. For example, barium chloride and sodium sulfate. Let's say we mixed those two solutions. First thing I need to do is decide which one of those became a precipitate. So if I write a word equation, it doesn't tell me very much. All I'm going to write is barium chloride and sodium sulfate, and then I'm just going to swap over the names of the metals so I get barium sulfate and sodium chloride. But it's very rare I'm going to get asked to do that because it doesn't really show me what chemical stuff is happening. So if it's precipitation, one of these products, either barium sulfate or sodium chloride, is insoluble. It's going to be barium sulfate because all sodium compounds are soluble. So I can now write a full symbol equation. There's quite a lot of formulae going on in this because I'm going to need to worry about barium having a 2+ charge, sulfate has a 2-, etc. And I've got to do some balancing because I've got 2 sodiums here and 2 chlorides, I've got 2 NaCl's. The main thing we can see is we start with a solution and another solution, and we end up with a solid, which is my insoluble substance, and another solution. So these ones are the spectator ions. Sodium and chloride didn't change. So when I write the ionic equation, I'm going to take out the sodium and the chloride. So I'm going to get rid of sodium and chloride. If I get rid of it from that side, and I'm getting rid of the 2, then I'm going to get rid of it on the left. So I'm going to get rid of the sodium. I'm going to get rid of the chloride. So basically I'm just left with barium ions reacting with sulfate ions to make barium sulfate. So what do I need to do? Well, I need to leave the charges on my ions. So if I'm taking Cl- away, I'm not taking just an uncharged substance. So I'm showing that the barium ions were at the start of the reaction. Remember that they were separate from the chloride anyway. The chloride was broken apart because they were dissolved. There's my formula for my sulfate ion, and then I'm just bringing it together to make a solid. So actually it's easier to write the ionic equation because I don't have to worry about all the balancing. I've just got a Ba2+ and an SO4 2-, so they cancel out nicely. Another example, let's say we mixed iron 3 sulfate and sodium hydroxide. Word equation again doesn't tell you very much. I'm going to pick my insoluble product, and it's going to be iron 3 hydroxide. This is a test for hydroxide ions, gives me a red-brown precipitate. So this is just to get you on side for ionic equations. As you can see, this is a nasty balanced equation because you've got an iron with a 3+ charge and a sulfate with a 2-. So you're getting this really awkward formula here on the left-hand side of Fe2SO4 And then you're going to need 3 hydroxides for every ion, and there's 2 ions, so you need 6 hydroxides. So the balancing is a nightmare. Let's see how that changes if we turn it into an ionic equation. Easy. I'm only worried about ion 3 hydroxide, so I don't need to worry about the sulfate ions anymore, which was making the balancing difficult. And so all I need to know is that I'm going to have 3 hydroxide ions because they have a 1- charge, and I have an ion 3+ ion to start with. And if you're very eagle-eyed, you will notice that I have missed the last state symbol there, which should be an S for solid. Don't do that, that will lose you a whole mark. So it's 1 mark for right formulae and balancing, and the second mark is for the state symbols, which is always aqueous plus aqueous makes solid.